Hello friends, welcome to this session. Today we are going to start the subject strength of material, and this is the introduction of the strength of material. Basically, the strength of material has various names in the various books also. So that solid mechanics also it is called as, and mechanics of the solids. So there are various names are there. So earlier we have studied in the engineering mechanics that there are different types of the forces which is acting onto the body. Specifically, we called that body it is rigid body. Very various forces are acting onto the rigid bodies, but we have not considered the deformation or displacement. We have not taken into account that displacement or deformation in the rigid bodies. Only whatever the forces are acting onto the rigid bodies and their reaction component parts we have studied in the engineering mechanics. But in this subject of strength of material or mechanics of the materials, we are going to study the deformation of the bodies. That's why that body it is also called as a deformable body. That's why this branch of engineering mechanics which deals with the behavior of solid bodies subjected to various types of the loads. That's why it is also called as mechanics of the deformable body. So basically we are just concentrating onto the bodies which is deformable, and after the deformation what are the different activities are happen into the bodies like a stresses which is developed after the application of the loads. So we are going to analyze those type of the different resistive forces from the bodies. So usually the objective of our analysis will be determination of the stresses, strains, deformation, which is also called as a deflection produced by the loads. If all these quantities like stresses, strains and deformation or deflection, if you able to find out for all the type of the loading up to the failure load, then we will have the complete picture of the mechanical behavior of the body. So this type of the these terms are important at the time of the design of any particular structure or machine component part. So a thorough understanding of mechanical behavior is essential for the safe design of all the type of the structures, such as in the civil engineering, building structure, bridges, in the some mechanical component part, machines, submarines, ships, or aeroplane and antennas. So these are the different type of the structures are there, which is in the field of civil and mechanical. So it is important to finding out the after application of the load on any type of the structure, the stresses are developed, the deformation it is happen into the body, and what are the extension it is happen into the body. So before going into the details, first of all we should know the historical development. The historical development of the MOS means mechanics of the structure. SOM means strength of the material is fascinating blends of both theory and experiments. So basically the experiments are carried out onto the different type of the component parts and members, and that's why it is a blends of the theory as well as the experiment. Firstly, the Leonardo da Vinci in 1952 to 1519 and Galileo Galilei 1564 to 1642 performed the experiment on the materials to finding out the strength of wires, bars and beams. Through they did not develop any adequate theory. He has performed they have performed the experiments onto the different type of the material like wires, bars, but they are not come up with the adequate theory on the onto this material after application of the loads. After that, Ehlers developed the theory for design of columns. So this is a historical part of the mechanics, strength of material or mechanics of the solids. Let us go into the first topic, that is a simple stresses and strain. Basically, the stresses already we discussed that the body is there, and there are different type of the forces and loads are acting onto the body, and body also offers some resistance onto these loads, onto these forces. So every material is in elastic in nature, in some part a little bit. Whenever some external force of system applied on a body, it undergoes some deformation. Means whenever the some external forces or system of forces are acting onto the body also react, body also offers some resistance, or it undergoes some deformation. Means in the body there are different fibers, molecules are present, the molecules set up some resistance to deformation. So definition of the stress, it is a resistance per unit area to deformation is known as stress. Also, it may in another way you can define the internal resistance against externally applied force is called as a stress. Mathematically, stress may be defined as the force per unit cross sectional area, that is stress. So symbolically the stress is represented by sigma, or in some reference book it is also small p, it is denoted by small p, is equal to p divided by a, where p is the load or force acting onto the body and capital is the cross sectional area of the body. So if you want to finding out the stress or resistance offered by any material or any member, you should know this formula, that sigma is equal to p by a. You should know the how much load is acting onto the body in Newton, kilonewton, and divided by the cross sectional area, in how much area that system of the loads is acting. So that cross sectional area, if you know, you can easily finding out the stress developed or resistance offered by that material. In SI system the unit of stress is Pascal, so we already knows this Pascal in earlier, that Pascal, the value of Pascal is equal to 1 Newton per meter square. In actual practice we use bigger units of stress like a megapascal. In the mechanics of the material or strength of the material, we require the bigger units like a megapascal or gigapascal. So that megapascal, it is also it is equal to 1 Newton per mm square, or simply Newton per mm square. So we'll see in detail about that unit conversion, or the different units are required for the strength of material to define the stresses. After that, strain. Whenever a single force or system of force acting on a body, it undergoes some deformation. So whenever the forces or loads are acting onto the body, though we have considered that the body is in elastic in nature, so there may be some deformation, or there may be some extension into the body uh, because of the stresses developed into the body. So in a single force or system of force, whenever it is acting onto the body, it undergoes some or little bit amount of deformation or or extension. So this deformation per unit length is known as strain. So we have studied the stress, means stress is the force or load per unit cross sectional area, and strain, it is the deformation or extension per unit length. So you just remember this strain. Mathematically, strain may be defined as the deformation per unit length. That is a strain. And strain symbolically it is represented by epsilon, or in some of the reference book it is small e also it is denoted. The formula already we have seen into the definition, that deformation or change in the length after application of the load to the original length. So simple formula, epsilon or E is equal to delta L divided by L. Here it is a delta L is a change of length of body. Delta L is also denoted by delta, means the change in length. So delta L divided by L. L is the original length of the body. So suppose the body may be a bar, maybe a wire, or any type of the structural member whose original length. So delta L, we can calculate that change in length after application of the load is epsilon into L. After that, the type of the stresses. So tensile stresses, when section is subjected to equal and opposite pulls. So in this slide you can see below the figure is there. Suppose the one bar is there, uniform cross sectional bar is there, and the forces are acting on both of the sides. So that is a pulling type of the force. When the section is subjected to equal and opposite pulls, the body tends to increase the length. Means there is an extension of the length. So there is an increasing of the length because of the pull is there on both the sides. So there is a magnitude of that pull is P, or force on both the sides in opposite direction, capital P, the magnitude of the force. So because of this type of the system, it is called as a tensile stress. So because of that, it body tends to increase its length, and whatever the stress is induced in this particular bar or in this particular member, it is called as a tensile stress. And whatever the corresponding strain or corresponding extension after pulling, that extension, it is called as tensile strain. In the second figure, below of the figure, you can see this compressive stresses. So instead of applying the tensile pull, we have to apply to the bar the compressive forces. There are two opposite forces, P again, but there is a compressive in nature. So that's why when the section subjected to equal and opposite push, a body tends to shorten in length. So whenever the opposite direction pushing type of the force on both the sides are applied onto the bar, then there is a shortening of the length of that bar. The stress induced into this particular member, it is called as a compressive stresses, and cross sectional area of body gets increased. So because of that, lateral dimensions of the pushing type of the forces, lateral dimensions are increases in these compressive forces, and in the tensile type of the forces, there is a longitudinal length of the bar or extension of the bar will increases. Shear stresses, symbolically it is represented by tau. When a member is subjected to load, it develops resisting forces. To find the resisting forces developed, a section plane may be passed through the member and equilibrium of any one part may be considered. So shearing stresses means any type of the bodies, whenever there is a loads or forces are acting onto the body, at that time there is a resisting forces from that body is also offered. So there are two types of the resisting forces are offered by the body. One type of the resisting force is the normal to the plane. You can see in this particular picture there is a whole body is there, and in this particular body there is a sectional plane is considered. There are different forces are acting onto this member, and if you see the sectional plane of this body, there are two type of the resisting forces. One is normal to the plane and another is a parallel to the plane. So whatever the normal resisting forces are acting, it is called as the normal to the plane or normal force, and whatever the parallel to the plane is called as shearing forces. So our definition of the shear stress is the resisting forces parallel to the plane. So resisting shear stresses means whatever the resisting forces which is parallel to the plane, which is called as a shearing resistance, or that is also called as a shear stress. So in this figure you can easily understand this type of the shear stress, the forces, resisting forces which is parallel to the plane. So internal resisting forces are developed because of the externally applied loads. So before in the in the earlier we have studied about the unit of the stresses, but when Newton is taken as a unit of force and millimeter as a unit of area, the stresses will be Newton per millimeter square, because we know that by the definition stress is defined as the load per unit cross sectional area. Normally the loads are defined or represented in force, and the unit of the force is Newton, and area normally we are represented in mm square. That's why our stress unit is Newton per mm square. The other derived units used in practice are also used depending upon the extent or depending upon the quantity of the material or area of that material, volume of the material. So either kilonewton per mm square, newton per meter square, or kilonewton per meter square are also used. The stress of 1 newton per meter square is known as Pascal. 1 Pascal, and it is represented by Pascal. So Pascal is symbolically represented by Pa. Hence we know that 1 Pascal is equal to 1 Newton per meter square. So if you want to convert this Pascal into, or if you want the unit of the stress in Newton per mm square, how you can convert that unit? So we know that 1 Pascal is equal to 1 Newton per meter square. If you take 1 megapascal, so mega means 10 raised to 6, mega means 10 raised to 6, so megapascal is equal to 10 raised to 6 into Newton per meter square. So 10 raised to 6 Newton. If you convert this meter square into mm square, so you multiply 10 raised to 6. So 10 raised to 6 and 10 raised to 6 cancel. So remaining 1 megapascal is equal to 1 Newton per mm square. Means from this we can say that the 1 megapascal is equal to 1 Newton per mm square. So you remember this, because in the coming problems we are frequently taking, or we are finding the stresses in the Newton per mm square or megapascal. Also sometimes for the huge structure, if the loading is more, at that time we can also our values or magnitude we have to derive into the GPa also. So we know that we should know the 1 GPa. So GPa means 10 raised to 9 Pascal, or 1 GPa is equal to 10 raised to 3 Newton per mm square, or we can also represent it by 1 kilonewton per mm square. So thus 1 megapascal is equal to 1 Newton per mm square, or 1 gigapascal is equal to 10 raised to 3 Newton per mm square. In most of the standard codes published, unit of the stress has been used as a megapascal. So that's why I'm telling you that most of the time for the most standard codes published in the different books, the stress unit is we have to take that is a megapascal, or in sometimes for the larger structure we have to take that unit gigapascal. So 1 megapascal is nothing but than 1 Newton per mm square. So today's lecture, this is only introductory part of the we can say the strength of material, and the very early simple stresses and strain we have studied here, and their units, their definition we have studied. Thank you very much.